Hello everybody and thank you for your attendance. My name is Marc Lieser. I'm with the Computer Vision and Mixed Reality Group of Rhein-Main University of Applied Sciences in Wiesbaden, Germany. And today I'd like to present our paper evaluating distances in tactile human-drone interaction. I will give a short introduction to the topic and talk about human-drone interaction in general. I will present the user study that we conducted and discuss its results before I end with a conclusion and propose future work. At the latest, with the first commercial drone deliveries approved by the FAA at the beginning of the year, UAVs are subjects of almost daily news and applications. Logistics, search and rescue, inspection, construction, measuring, and aerial photography or videography, to name just a few. Because of their simplicity and affordability, quadrotors have become the aerial vehicle of choice in the hobby area, in research, and in commercial applications. In the future, they could offer their services to humans at home or at work, just as flying robots already support astronauts in space today. Whether future or already present applications, the increasing number of drones requires more natural ways of interaction than classic radio remote controls that are only used by professionals and hobby pilots. So researchers have studied interaction methods at different distances. At far and closer distances, body and hand gestures can be used to control a quadrotor, but also experiments with facial expression and voice control were conducted. At immediate proximity, touch interaction has been implemented, and tap interaction detected by a quadrotor's onboard inertial measurement unit has been proposed. But to allow for physical close proximity quadrotor interaction, humans must grant the robots access into their personal or even intimate space. And for this reason, we would like to take a closer look at the proximity and acceptance of small flying robots. The research field of proxemics addresses the way and distance robots approach humans. Interpersonal distances are divided into intimate space, personal space, social space, and public space. Most of interaction happens in personal space. Previous studies show that ground-based robots are allowed to get closer than flying robots, and that flying robots with social features are allowed to get closer than those without. But user studies are hard to compare because of differences in setting, context, location, the quadrotors themselves, and the way they are controlled. In previous studies, not all of them were actually flying, but being moved. But rotating rotor blades and the noise and downwash they generate certainly have a strong effect on people and their inhibition threshold. In other studies, quadrotors were controlled by a human pilot or by onboard control, which resulted in non-repeatable flights. Repeatable flights can only be realized using state-of-the-art motion capturing systems used for pose estimation. Quadrotors also differ in their appearance, including the fact that some of them have a frame that serves as a rotor guard, which also increases the level of safety of the humans. Larger quadrotor platforms trigger increased mental stress and are stopped before they get within reach of the user to actually allow for physical interaction. Before further exploring tactile human quadrotor interaction scenarios, we wanted to find out if this is still the reason with smaller platforms. So we conducted a user study. One hypothesis of the study was that people would display different levels of effective responses and comfort with different approach directions. This was assessed through questionnaires and the measured stopping distances. The second hypothesis was that people aren't inclined to physically interact with the quadrotor by hand, which was assessed through the proportion of hand-stopped flights. So the user study was conducted with 32 participants from our institute. Since we aim at future home or workplace scenarios, we went for a seated setting. The quadrotor approached from 4 directions, namely the front, back, left, and right, along a straight trajectory in a randomized order. Overall, we conducted 128 flight approaches, and the participants were left the choice to either stop the quadrotor by a provided foot switch or by hand as soon as they would start feeling uncomfortable. And for safety reasons, the head quadrotor distance was continuously monitored in order to interrupt the flights when the quadrotor would get too close to the participants' heads. This figure shows the laboratory setting. We have multiple pose estimation cameras mounted to the ceiling to track the quadrotor. The quadrotor, as seen on the right, has a 3D printed frame to provide interaction points marked with arrows. A Kinect 2 tracks the participant skeleton, and all cameras are registered into a global reference system. Thus, the tracked quadrotor pose and skeleton joint positions are provided in reference to the same origin. In a session that took about 20 minutes, the quadrotor would lay at the origin, was then instructed to take off to the start position, and after a verbal confirmation of the participants, it would move along its trajectory toward the participant until they stopped it. So 128 flights later, let's have a look at the results. The slide compares distances to related proximity studies conducted with quadrotors. The largest platform used was an Aerobot AR100B and the first proximity test conducted using a drone. It was mounted to a movable platform, so not actually flying. The second one was a non-social, which means a regular looking DJI Phantom. The third one is a social DJI Phantom, which means it was provided with a face and a greeting voice. Both were moved along a zip line. The fourth approach is a Parrot AR Drone 2 that moved autonomously, but the authors noticed irregularities in the trajectories, which is due to onboard pose estimation accuracy. The fifth one, an Ascending Technologies Hummingbird, was actually flying and was tracked by a state-of-the-art pose estimation system comparable to ours. And the next two incoming quadrotors are from our own experiment and show the average stopping distances when stopped by foot or hand respectively. Over all flights, 68% were stopped using the foot switch. 8% weren't stopped at all because the participants wanted to find out what happened if they wouldn't intervene. And only 24% of all flights were stopped by hand. So overall, the quadrotors were significantly less often stopped by hand than by foot, as well as for flights approaching from the back and from the left. The box plots on the left show all sampled flights color-coded by the stopping method. For the sake of completeness, here is a table with the mean values and standard deviations of foot and hand stopping distances for the individual directions. Note that the flights approaching from the back are stopped later than the others. After each flight, we asked the participants 2 questions provided as 5-point Likert scales. The first was about their well-being and the second about their perceived final stopping distance of the quadrotor. Results show a significantly decreased level of comfort when the quadrotor approached from the back. In addition, the final stopping distance was perceived as being too close. There were no significant results for the other directions. The user's emotional states were assessed using the self-assessment mannequin scale once initially and then after each flight. A Wilcoxon signed rank test showed a significantly increased level of dominance for flights approaching from the front and a significantly increased level of arousal for flights approaching from the back and from the right. So we conducted a user study evaluating basic distances in human-drone interaction, also researching the participants' inclination to physically interact with a miniature-sized quadrotor. Distances that extend into intimate space without detectable increased level of mental stress, and that some users found joy in tapping the quadrotor's frame in a playful way, encourages us to further explore tactile interaction in more elaborate scenarios and different contexts. And in order to further lower the inhibition threshold, we are currently also working on generating trajectories that are able to convey a quadrotor's intent. Thank you very much for your attention, and let's meet in the Q&A.